Greetings, physicists. This video will be about solving problems involving uniform circular motion. So we'll start with speed skating. Apparently, if you are an Olympic or world-class speed skater, you can do 500 meters in 45 seconds. And we're going to talk about the turn, very short turn. Our classroom, for instance, is about 12 meters wide, and which seems pretty wide for you, but you're used to walking it. So if you're going as fast as these ladies are, you're probably going to have a tough time with it. So let's see. It says estimate the centripetal acceleration they feel during that turn. I'm going to draw it real quick. So we'll have a little turn that they have to go around here. We'll pretend that I drew it like a circle, and we'll say it's an 11-meter radius circle that they sweep out. Well, some givens. Let's look at this. We have the total length of the track is 500 meters, and they can do that in 45 seconds. So I think the reason that's going to be useful to us is we can get an average speed. Now, obviously, there are going to be points where they're going faster. The straightaway, they can go faster than on the turn. But let's just average it out, and let's just say that their average velocity would be the total distance that they travel in the total time, and that for these skaters is 500 meters in 45 seconds. So a quick calculator bit here should say 500 over 45, about 11. If I round it, it's about 11 meters per second. Pretty fast. I think Usain Bolt can run it like about that much. It's like 10 point something or 11 point something. So they're going fast. All right, other givens we have. We have the track itself is 11 meters, so I'll put that down here. The radius of that track is 11 meters. We have the average velocity around that curve is going to be about 11. Well, that's good. That's convenient. And no, there we go. We're looking for, our unknown is acceleration, and I'll say it's a centripetal acceleration, because it's the acceleration that causes them to go around that circle. Well, that is pretty easy, because our equation is centripetal acceleration equal to v squared over r, and we have both of those things, and we don't even need to isolate the AC. That's already done. So let's just plug and chug. And these numbers happen to be easy numbers, so we'll have on top 11 meters per second, and we're squaring that over a radius, which is 11 meters. Okay, well, 11 times 11 divided by 11, right? So you're going to have to just get rid of that. Meter squared over second squared divided by meters, so we'll get rid of one of the meters there, and we should get leftover of about 11 meter per second squared. So the numbers didn't turn out to be super interesting here. But let's put that in perspective. You right now are feeling an acceleration, or as if you were accelerating downward at 9.8, right? So gravity is 9.8 meter per second squared. So when these skaters are going around that curve, they're essentially feeling 1g of sideways acceleration. And so one thing, if you've ever watched Olympic speed skating and you see them going around the curves, they look like this. They're like almost like, here's the ice, and their legs and their body are like almost completely sideways as they go around those curves. And they can do that because that centripetal acceleration is bigger than gravity. Really neat sport. All right, let's go on to our next one here. So you're a road engineer, and engineers who build roads like circles. They like to design curves to be circles. They like dips and peaks, like bridges and things that are all segments of circles. And they can make the radius of those circles different depending on how fast they want you to go, right? Think of speed bumps. So we're looking at a car that's going to be going into a dip, and we're curious. So let me draw the dip. Here's a here we go. Here's the road. Some engineer designed it, and the car is going to get to the bottom of the dip, moving along there, and it says, is the normal force on the car bigger, smaller, equal to the regular weight of the car? Good deal. So let's do a free body diagram for the car. The car has an mg down. It's going to have a normal force up, but it's not traveling on a flat surface. It's traveling around a circle, essentially. And at any point, to stay in that circular path, because the curvature of the road changes every instant, there will be an acceleration. There will be a centripetal acceleration. So suppose this is the center of that circle of that road. There is an acceleration in that direction. And because there's an acceleration in that direction, some force must be causing that. So there is a centripetal force that has to be applied to keep that car moving in that circle. So at the very bottom here, let's think about that. If the normal force were just equal to mg, that would only be enough to balance out the car's mass, but we also, that would be true up here, right? When the car wasn't on the circle, the normal force had to balance out the car's mass. At the very bottom of the circle, the normal force also has to accelerate the car upwards. So there's an upward acceleration to this car. So it has to beat gravity and accelerate the car upward. So unlike up here, this car is not accelerating upward. This car has zero upward acceleration. This car has some upward acceleration. So I'm going to have to make that arrow longer to achieve that upward acceleration. Because if it's just equal to the normal force, there wouldn't be an upward acceleration, and this car wouldn't make it around the curve. So at the very bottom of the dip, is the normal force greater than, less than, or equal to the car's weight? It's got to be greater than, or this car would not be traveling in that curve. Conceptual problem. Love it. All right, another conceptual problem. This time we're looking down on a car. So here's our car from the top view. And this car is traveling around a curve, around a corner. And it does so at a constant speed, and it is tracing out a circle as it does so. What force causes the acceleration? So if it's actually in a circle here, if we do this, there is an acceleration. It's this way, towards wherever the center of that circle is. So there must be a force that causes that acceleration. What's pushing on that car? It's not gravity. If we're looking down from the top, gravity is away from us. We would draw that like this. So it's not gravity. It's a force that's going perpendicular to gravity, or perpendicular to the normal force. The normal force comes straight up at us, so we would draw straight out like this. So let's try and draw this car from the side. Maybe that'll make it easier, especially if we haven't dealt with that notation yet. So from the side, if you were looking at the back of the car, right? Here's the car, here's the tires, and it's the curve. It's going to be making a right-hand turn here. We have the mg pulls down on it. The normal force pulls up on it, but whatever's causing the acceleration is pushing to the right, and of course it's sitting on the ground. Well, the only thing that can be pushing on it really is the ground, because it's touching the ground, right? There are no other things touching it unless you think the air is doing it, but I guarantee you that's not the case. So what's happening is, if you've ever noticed, like if you're looking down on this car, let's go back up to my top down. When you want to make a turn, right, your tires, I'll draw the back tires, are normally faced forward like this. When you want to make a right-hand turn, you take your front tires, turn them like that. And now, as your car moves forward, the edge of these tires, this leading edge here, is rubbing against the road. And so there's a push against that, pushback from the road as you do that. That's a frictional force. So the force that pushes you around a curve is friction. The road pushes you in that circle. If you could think about that. Okay, there is our number 3, our conceptual problem. Let's keep going. So using that concept now, let's talk about a car. Let's put some numbers to it. We're going to make the same situation. So we've got the car. Here's the car going around the curve. Pretend I drew a nice circle curve. Of radius 20 meters, so we'll say that the center over here is 20 meters away. All right, and we're going to claim this is a 1,500 kilogram car. It's a relatively small car. Maybe like a Camry or something. And we want to know how fast it can make this turn. Now, this is a tricky problem, but let's go ahead and give some numbers here. Let's some givens. We have a mass. Well, I can just write it over here. Mass is this, 1,500 kilograms. We have the 20 meters. That's our radius. Our unknown is v. And it doesn't look like we have enough, right? We would need a force equation here, but fortunately, what we learned in the last problem was that we know friction is causing this. So if we can figure out a friction, we can solve this problem. Now, this is a leap here that you would have had to anticipate. The friction is between tires and asphalt. The tires of the car hitting the asphalt. So what you would need to do is look up the coefficient of friction between rubber and asphalt. And it's not really intuitive, but it would be a static coefficient of friction. So mu static between rubber and asphalt. Turns out that's very high on purpose. That's what makes cars go. So we have a 1.0. If you go on a engineering toolbox and find it, that's fine. And this should be enough for us. It's going to require a few equations, so let's make a list. We need the centripetal acceleration equation, v squared over r. We need the force equation, F equals ma. And we need the friction equation, mu normal. And I think with all of those, we should be able to get where we're going. So let's try and solve this up. We want v squared, or we want v. We want the maximum speed this car can go around the curve with. So I'm going to solve for v and say that v should equal the square root of ar. Well, I also have this equation, which if I solve for a would be f over m. So v is also going to be equal to the square root of fr over m. And now we need a free body diagram to get that force. Well, if we're looking from the side or the back, we had a normal force straight up, we had an mg down, and towards the center of the circle is that frictional force. And that's the force that's causing this acceleration. So that's really the force we've got to use. The normal and the mg are going to cancel each other out. And that frictional force is equal to mu times the normal. So let's put that into this equation here. Let's say that v will be equal to the square root of mu n r over m. That n, though, we can see that from our free body diagram, should be equal to the mg. So we can say that's the square root of mu mgr over m, and lo and behold, that mass will cancel out. And that's useful. That's why we do these solve ones first before we start plugging things in. So my maximum velocity, if I'm an engineer and I'm designing this curve, should be the coefficient of friction times g times the radius, and we square root that. Not too bad. That's a static coefficient of friction that I would need to know. And I think we have all of those. So my static coefficient of friction was 1, my g is 9.8, and I have a radius of curvature of 20 meters. Let me put that in meter per second squared there. All right, so I'm just square rooting 9.8 times 20. 9.8 times 20, square root. Oh, it's a perfectly round number of 14 Let's see, we have meters times meters is meters squared over seconds squared, so I'll be left with meters per second after the square root. 2 sig figs is fine for this problem. Okay, well, let's think about it. 20-meter curve is similar to what you would see if you were at an intersection. And if you're a driver, you probably recognize that going around a 20-meter curve at 14 meters per second, that's even probably fairly fast. If you think that 29 meters per second is freeway speed, that's half of freeway speed, so that's like a 35 miles an hour, 30 miles an hour. Yeah, you probably don't want to take a curve at 30 miles an hour in the intersection. You probably do less than that. Because if you go farther than that, if you go faster than this 14 meters per second, that coefficient of friction is not big enough, and you'll slide. Also, this coefficient of friction goes down when there's been rain and things like that. So you also have to be careful if you're in a wet environment, because then you can't go as fast or you will slide. Physics. All right. Going on to our next one here. All right, so that was a flat curve. Now we're going to talk about if you ever go to NASCAR and you watch the cars going around the track. It's a big, long oval track, right, like this. And then if you look at this part of the track, it's banked, right? And the cars are coming around. Let's see if I can draw the front end of a car. Probably can't. There, beautiful drawing. Little NASCAR driver in the front. They're banked, and that actually helps. It's going to make it easier for you to go around the turn, or it's going to make it so that you can go at a higher speed without slipping. So let's look at this problem. We're saying what speed can a car take a curve, assuming that this particular curve has a 15-degree angle that it's banked to. And that the radius of that curve, if we were to look here, like the radius to the center of the circle that makes that curve from the top down, is a 70-meter radius. How fast can we go without assistance from friction? And we'll talk about what that means as we go through this problem. Well, these are difficult problems to visualize because you have to do them in 3 dimensions. And there's not a lot of what we do at this level of physics that's in 3 dimensions. But let's talk through it here. We have some givens. We have a radius of curvature of 70 meters. And I drew it here as the center of a circle. Here, that center of the circle is in this direction. That's that 70 meters. Okay, we'll call that the R. And we have the 15-degree angle. They don't give us the mass of the car. Now, that might seem like an issue, but if you remember in the last problem, the mass wound up canceling out. So let's hope that that is what happens here. The tricky part of this is going to be drawing a free body diagram. So I'm going to try to draw it for this situation as if I'm looking at it from the side. And my free body diagram for this guy will look like this. I will have gravity always pulling straight towards the center of the Earth. Now, if you picture him, he's on this angle, so the normal force is going to be off this way. And I don't think there's any other forces on there. We said in the absence of friction, so there isn't going to be a friction force. So that's it. Well, what you want to avoid doing is what we did with every other incline problem you've ever dealt with. For instance, we used to do boxes sliding on inclines. And when we did those free body diagrams, there was a normal and an mg, and I had you rotate them so that the normal was up and the mg was this way. The reason we did that is because we had to line up with the acceleration. The acceleration was to the right, or was this way, right? There was an acceleration down the ramp, which was in this direction. And so we rotated so the acceleration lined up with the x-axis, and then the normal lined up with the y-axis, and that meant that the mg was the one that had to be resolved into component forces. That's not what we're doing here. If we go back up here, and I'm going to try and lay this out as much as I can. From the top as the car goes around like this, we're going to assume that that car goes at a constant speed. So it is not accelerating in the plane as viewed from the top. It's not accelerating left and right. It's not accelerating these ways, so like north, south, east, west. So that means that in this plane, when the car comes towards us, it's not accelerating towards us or away from us, and it's not accelerating or like that. What we will say, because this 70 meters, right, represents the radius of a circle, in order to maintain that curvature of that circle, it does have to accelerate towards the center of the circle. That's a centripetal acceleration. Look what direction that is if I draw that on my free body diagram. It's not really part of the free body diagram, it's just here. This is that acceleration relative to my free body diagram. So it is on the x-axis already. This does not require tipping. You can just leave your free body diagrams the way they are for banked curves. So the mg, which is already up and down, already lines up with the y-axis. What we need is for the normal force to line up with the x and the y-axis. That's the part you're going to have to get over when you're talking about banked curves. Now once you've got that, the rest of this is not so bad. So I'm going to redraw because I just drew a bunch of lines and that made this messy. So let's give us a nice clean start here. So we had the car here. We had the free body diagram for the car with the normal and the mg here, and we had the angle here is 15 degrees. What I need to know is that angle this angle or this angle? And that way I can split my normal force. So here's how I prefer to do this. That 15 degrees is with the horizontal, and by symmetry that means that if I were to draw the angle up here, that 15 degrees would be right there. Now let's draw a complete vertical that just passes through the right hand side there. And let's draw the normal. The normal would be here. Now that normal is at a 90-degree angle, right? A 90-degree angle with the surface, which means that here, so watch, 15 degrees here. This angle here, which is part of a 90-degree angle, would be 90 minus 15. Right? But because this part here is also 90, that means that this is a 15. Satisfy yourself that that is true. So that means that I'm going to make this triangle, I'm going to split my normal into a vertical and a horizontal, and that is the 15 degrees right there. So whatever you have, if the track is banked with the ground, make that your the angle between the normal force and the vertical. And so now we can see that the vertical line here is the adjacent, so that's the cosine line. So I'll do n cosine 15, and the horizontal line is the opposite, so that's sine, so that's n sine 15. That's the hard part of this problem. If you can get that done, I think the rest of this is a lot more straightforward. So now that I have my free body diagram, I can do sigma f's. That's what I need. So my sigma f, let's do the vertical first. I have a normal cosine theta up, and I have an mg down. And the car is not accelerating up or down, right? The car here is just staying put on that track. It's not leaving the track, like bouncing up in the air or something. So we will say that n cosine theta, in this case, equals mg. And then we can do the horizontal, which says that n sine theta. Well, really, that's the only right-hand arrow. There's no left-hand arrow. So that's going to just be equal to ma. There is an acceleration in the horizontal direction. In the vertical direction, there was none, so those two things we can set equal to each other. And we have, right, that's F equals ma. We also have our friction force equation. Friction equals mu normal. Good stuff. So let's kind of resolve all of these three equations here if we can. I'm going to say let's start with this one. I can solve for n and get n equal to mg divided by cosine theta, which I can then plug into that. So I can say that I'm going to say mg over cosine theta times sine theta equals ma. Oh, I did the friction equation. I don't even need it because we said there was no friction in this problem. All right, look what I can do. I can cancel m off of both sides. And I can make the sine theta over cosine theta equal to tangent. So we can say g tan theta equals centripetal acceleration. Oh, you know what I do need? I need the centripetal acceleration equation. AC equals v squared over r. So let's do that. So g, that's more room here. G tan theta equal v squared over r. And that's originally what we were trying to solve for. We wanted to know how fast can I take this term without using friction to help me. So let's solve for v. V should be equal to the square root of g tan theta r. And all of those things should be given to me. If we go back and check, well, we know g, square root of 9.8 meters over second squared. We know tan theta, that's tan 15, and r was a 70-meter track, right? 70 meters. Well, I'm going to have meters times meters is meters squared over second squared. When I root that, I will get meters per second, so I'm in the right units, and now I just have to do my square root. So it's going to be square root of 9.8 tan 15 times 70, and I should get, well, what I get is about, that seems low to me, but I'm in degrees. All right. So I'll tell you what I'm getting and why it seems weird. 13.6 meters per second when I round. The reason that seems weird to me is because that doesn't sound like a race car speed. It sounds like just a really easy, regular old road speed. Nope, but I'm checking, and that is the correct answer. Now let's look at our Sig Figs. I've got 2 here, 2 here, 2 here. Let's go ahead and round that to 14. Round it to this place, 14 meters per second. So a race, if you were on this particular racetrack and it only had 14, or it only had a bank of 15 degrees and a 70-meter radius, you would only be able to go 14 meters per second, which is like half of highway speeds. So fairly low. This could be on a more complex track, perhaps. Also, we did say without friction. So let's talk about how friction changes this. Because it does make a difference, and those race cars have high friction tires. Where's my picture? There's kind of my picture. So if you're a race car and you go around that track at exactly 14 meters per second, you will not slide on that track, no matter, even if there was no friction at all. If you were doing this on a polished marble track with steel tires, something that slides very easy, you would not slide if you went at exactly that speed. If you try to go faster, though, your car, in the absence of friction, your car would start sliding up the incline, because a faster speed corresponds with a larger radius. So your car would naturally try to go to the larger radius. And if you were trying to go at a speed lower than 14 meters per second, that's not enough speed to maintain this radius, and you would actually start sliding down the track to a lower radius. So you can make that turn at a higher speed, assuming that your tires have enough friction to hold you on that path. So that's how that works. Okay, that's banked curves. And there is a way to solve this with friction. It just becomes several orders of magnitude more difficult. which I will probably do in a separate video. Okay, is that it? All right, last one. Vertical loop this time instead of a horizontal loop. So the race car drivers, they're just driving around in circles on the ground. The motorcycle guy and the Daredevil, sometimes you see those guys that are in the big, it's like a motorcycle cage, right? And the whole thing, there's like a big cage and the guy's riding his motorcycle like this, upside down in the cage. That's hardcore. So what we're looking at, he rides his bike around a 2.2 meter vertical loop, and he controls the bike by having, again, friction is what lets you steer, right? Friction between your tires and the ground, which in this case the ground is the loop itself. So in order to have control of the bike, at the very top of the loop, he wants the normal force on the tires, which is what's going to cause the friction, to equal or exceed his and the bike's combined weight. All right, that's hardcore. How fast does he have to go? So I'm going to draw a simplified version of this without the cage in it. So let's say he's just going in a vertical loop. And at the top, that's where he's going to be. Gosh, let's see if I can draw this upside down. There we go. Let's do a free body diagram for him. And what we know is gravity is going to pull him this way. And he wants to have a normal force that is the same as or greater than the weight. So I'm going to draw it basically the same length. Like that. And we'll say that mg is him and the bike together. All right. That's the case. I don't think there's anything pushing him upwards at all. He's definitely accelerating downwards. So let's see what equations, well, what givens did they give us? Did they give us anything? The 2.2 meter vertical loop. Okay. So we know the radius. Is that a radius or a diameter? Good question. I think you could actually interpret this either way. A 2.2 meter vertical loop. If it's 2.2 meters is enough for him to fit. I'm going to go ahead and claim that's a diameter. I think they're saying that the whole loop is this 2.2 meters tall, and let's solve it from that perspective. So the radius of this loop is actually 1.1 meters. Okay. What we need the centripetal acceleration equation. V squared over r. We need the force equation, F equals ma. And I believe that is it. And we'll have our free body diagram as well. So let's do the free body diagram first and plug that in for it's a sigma f, right? So the sigma f is these two things added together. And we want the normal to be, well, we could also write this. We want the normal to be equal to mg, or bigger than. So I'm going to say that at the very least, the normal has to be the same as mg. So if I do my sigma f, and they're in the same direction, I don't have to worry about direction here because they're both downward. So if I do my sigma f equation first, I have the normal plus mg, which is the same as saying 2mg, because they are the equal. 2mg has to equal ma. All right, that's the sigma f part. And look at that. M cancels. Sweet. So the acceleration has to equal 2g. Well, I can put that in here. The acceleration is a centripetal acceleration. So I have 2g has to equal v squared over r. And now if I solve for v, which is what I'm looking for, how fast he has to go, he's got to pull 2 g's, essentially. That v should be the square root of 2gr. And that will give me what I need. So that's square root of 2 times 9.8 meters per second squared. And the radius was 1.1 meters. All right, let's see what the calculator spits out here. 9.8 square root 4.6 meters per second. 2 sig figs? Yeah, 2 sig figs. That's not that fast. I mean, some people can run that fast. I would say a lot of people can. So if you've ever been at a circus show where you watched the motorcyclist ride around inside of a steel cage, a circular steel cage, he may not have been going that quickly, and this is why. I mean, you could go faster than that, but if you go any faster, you're going to pull more G's. So remember, if you go above 2 or 3 G's, you start to red out. If anybody's ever ridden one of those roller coasters where you're feeling like 3 times the acceleration of gravity, sometimes it's hard to keep blood to your brain. So going at the minimum speed is in your interests. You can only imagine how much these guys have to practice so they don't injure themselves. Dangerous stuff. All right, there you go. Hopefully this is helpful in your endeavors to solve circular motion problems.